Okay, today we will talk about climate models. So there are a number of different facets of climate models, and I like to categorize them by complexity. So I'll draw a complexity spectrum up here. So we have low complexity on the left-hand side and high complexity over here. So on the left we have very simple climate models, on the right we have really complex ones. So let's look at some simple models, and they are also sometimes called idealized climate models. And you have come across a couple of these already as part of this course. So remember when we had Earth represented by just a simple dot. This is what you would call a zero-dimensional model, where you just consider a balance of incoming solar radiation. And we learned that here solar radiation is 340 watts per meter squared roughly. And this is balanced by long wave outgoing radiation. And the long wave outgoing radiation, let's say F out, is given by the Stefan Boltzmann law, sigma T to the 4. So you can balance the energy fluxes. F down has to be equal to F up, and F down is alpha S, where alpha is the albedo, and that has to be equal to sigma T to the 4. And you can solve this for the surface temperature, Ts, as alpha S over sigma power of a quarter. And so this really is the most simplistic climate model that you can think of. It's a zero-dimensional model. So what would be the next stage on our complexity spectrum? Well, here we can consider some one-dimensional models. And before I talk about one-dimensional models, let me just say the reason why we use idealized climate models is because sometimes we want to understand certain aspects of the climate without going into great detail of all the different complex processes that are going on. And as we learned, if you just do a simple energy balance like we've done it here with the zero-dimensional model, you get actually a fairly accurate surface temperature out of that, because the dominant processes that set the surface temperature of Earth are the incoming solar radiation and the outgoing long-wave radiation. Now, there are many different components of the climate system that produce regional variations, time variations, etc. And so if you want to get a handle on those variations, you increase the complexity of your climate model. So the next level is a one-dimensional model. And there are two types that I'm going to highlight here. The first one being a single column model, and that is vertical. And so in a single column model, you just consider one column of your climate system. Let's say it is a spot over the ocean, and sometimes a single column of your climate system is fairly representative of a whole wide region of an ocean. Yeah, so you might only be interested in how the different atmospheric layers are connected. So you would, for example, represent different types of fluxes. So you have F atmospheric fluxes, and then also down here you might have a ocean layer, and then below you have oceanographic processes. So here you would have ocean fluxes. And so you can, for example, represent vertical motion or vertical energy fluxes, etc. in this single column model. And if the region of the ocean doesn't vary much spatially, then this gives you a really good idea of what the vertical structure looks like. Now, another type of one-dimensional model is if you're looking at a horizontal, for example, a diffusive energy balance model. So in this case, you don't consider the vertical structure, but you only consider a 1D horizontal structure. Here we, for example, could have the equator on the left and the pole on the right, and then your model represents a number of grid boxes corresponding to different latitudes, and then you can resolve, for example, different solar incoming radiation, which, as expected, would be highest near the equator and lowest at the poles. And this would be balanced by outgoing long-wave radiation, which also would be highest at the equator and lowest at the poles. And now you have a temperature gradient from equator to pole, so that would introduce some heat flux from the equator to the pole. So you would have horizontal heat flux, whereas the yellow incoming solar radiation and the red is outgoing long-wave radiation, OLR. So that's a type of one-dimensional model that is essentially the next level of complexity from our zero-dimensional model. So you basically do more or less the same calculation as you did before, but now you account for the fact that the Earth has horizontal structure. The next step here would be a two-dimensional model, for example, where you don't just look at latitudinal variations, but you could also think of this as having a second dimension. So you're looking at a surface with zonal variations. But I won't go into this detail. The next set of models I wanted to talk about are so-called EMICs. EMICs are Earth system models of intermediate complexity. And this is where we're starting to go towards comprehensive climate models, which is on the other end of the spectrum compared to idealized climate models. And you typically consider global climate models here. And so a comprehensive global climate model tries to represent every process that is relevant for the climate. An EMIC is sort of 2/3 of the way there. So an EMIC tries to resolve the full globe and partitions this into a number of grid boxes. And then for every grid box here, you solve the momentum equations for your atmosphere or ocean, depending on whether you're looking at a atmospheric cell or in the ocean. You solve for conservation of mass and conservation of energy. And you impose boundary conditions, such as a land surface or bathymetry, and also forcing conditions, such as incoming solar radiation or greenhouse gases, aerosols, etc. Now, what makes an EMIC different from a comprehensive global climate model is that this resolution is pretty coarse. So here your latitudinal and zonal resolution is typically on the order of something like 10 degrees per grid box. So obviously if 10 degrees is thousands of kilometers, you're not representing a large number of smaller subgrid scale processes. And the idea with a global climate model that is more comprehensive than that is that your grid becomes finer and finer, and you're starting to explicitly represent as many processes as you somehow can. And in the next video, I will talk in a little more detail about comprehensive global climate models.